Today I want to talk about different concepts. I want to talk about fluctuation, dissipation, diffusion, and finally, so we will tie these things up together, and finally I will, if I have time, I will talk about friction, which is related to dissipation, in fact, right? So let's start with a code. So you remember our code, we had a room filled of balls bouncing off each other. Do you remember that code? So now I will add a big ball, okay, that has larger mass and larger size, okay? And let me show you how I actually added that. So now actually the particles have masses, particle mass, okay, the tiny particles. This is the the giant ball mass. Does it make sense?
In the earlier example, didn't we give mass to the particles?
Yeah, we gave 1. We set everything to 1. Do you remember?
I forgot.
Okay, so this is the velocity of the ball. So there will be just one ball. This is the coordinate of the ball. And this is just the path of the ball. So basically this PB will keep the RB data with respect to time. I will use it for plotting. This is the diameter of the ball. And then what this one does is find, okay. Are you with me, by the way? Yes? Find particles inside the ball. So we don't want to start with particles inside the ball, right? Then this line will put particles outside the ball. Does it make sense to everyone? And do you understand how it is done? Basically, let's say you know that they are already inside the ball, like there is a particle inside the ball. You you take it out by moving it in any direction with d plus d ball. Okay, any direction, then you make sure that it's outside. Makes sense? So random theta, then you add this d times cosine theta sine theta.
May I ask something?
Of course.
How do you make sure that the particles don't merge into each other?
I don't make sure that they could merge together, but our algorithm is like if they are inside each other and if they are moving towards each other, then they will bounce. If they are not moving towards each other, then they will just separate. So at the beginning there is something unphysical going on, but it quickly handles itself. So the main difference in this program is the bouncing between, so let me just type this part, or in this part, particles bounce off the ball, and vice versa. So particles bounce off the balls and ball bounces off the particles, right? You may wonder, where did I get this formula. I think we take too much time, less time, to describe the collision with two equal masses. This is just the same philosophy, collision between different masses. This is moving particles, this is moving the ball. Do you have any questions so far? No? So let's run this and see what happens. So you have a ball, and I'm actually plotting the trajectory too. Do you see the trajectory? Do you see that because of the kicks, the ball is moving by itself, right? Is there anyone who knows what this motion is called? Yes, it's Brownian motion. Biologists like to talk about this stuff. And let's just glance into some papers very quickly. For example, one of the Einstein's miraculous year papers concerns this Brownian motion, right? He discovered a relationship between the fluctuation and dissipation, and I will come to that in a moment. I really recommend you to read this paper and explain it to me. Okay? Basically, he claims that if the motion to be discussed here can actually be observed together with the laws it is expected to obey, then an exact determination of actual atomic sizes becomes possible. So he basically connected molecular heat, kinetic theory of heat, to the movement of, to the Brownian motion. So if you investigate Brownian motion, which is easy to do with a microscope, you can know something about the sizes of atoms. Okay? So today I will use some relationships, especially I really recommend you to watch this video by this person, Jos Tishsen. I hope I'm pronouncing his name correctly. And he generously actually uploaded his notes on Brownian motion. And today, instead of deriving all this, I will share actually these notes with you. And we will validate this. We will validate the things that theoretically are found numerically. Okay? So let me still talk about it a little bit, what it means. In the meantime, we can stop the code. You can see that it's doing this Brownian motion. So let's think about it. So it's an object and particles are bouncing off this object, right? And if, let's say we want to write an equation of motion for this large object, okay? So we want to write F equals ma, okay? Ma is easy part, m times v dot. Do you agree? Everyone? Yes. So one of the effects of bouncing from these objects is that if this one has some velocity, let's call it v ball, okay, then let's say a particle bounces off this part or this part, which one will deposit more momentum?
Deposit
into the ball. Uh, this one, right? The one, this one will put like, okay, So it will, okay, let's say it's moving initially with v from here and with v from here. So this one will bounce back with velocity v minus vb,
Yes.
right? But this one will bounce back with v plus vb. Do you agree? And the kick that this one gives to it will have to do with mv plus 2vb, as we discussed earlier with the wall. You remember? Did you follow this part? Yes? And this part will have to do with mv minus 2vb. Of course, there are some other things, maybe some other corrections, but I just ignore them. Yeah, so what I'm trying to tell you is that the ball in the direction that it is moving, it will get more kicks. Does it make sense to everyone?
It will, but for, I mean, so you derive bouncing particles velocities, right? So if the bouncing ball is in the direction of the
Yes.
bouncing particle is in the direction of the ball's velocity,
yes,
then it will return back with the v minus vb velocity.
yes,
But if they're opposite, it would be v minus vb, right? Check v plus vb, right? I'm just repeating the things you just wrote down.
yeah.
Bouncing speeds of the particles.
My main point is that it will get more kicks in the opposite direction that it is moving.
You said deposit momentum.
Deposit momentum, yes.
So if a ball bouncing off returns with a bigger speed than its approach speed, then it means that it has got more energy, right?
Yes.
The particle. So that our ball actually lost some energy. Whereas on the other case...
Yes, exactly. Depositing momentum doesn't mean that it can't lower the energy. That's the whole point. Okay, if you are right in a sense that if the ball is moving in this direction, right, yes, and gets a kick from here, yes, its energy increases. Yes. If the ball moving in this direction gets a kick from here, its energy decreases. And my whole point is that these particles, this bouncing, will decrease the energy of the ball. It will act as dissipation.
What I understood from depositing momentum into the ball is like adding energy.
No, if your momentum is in this direction, right? You have this much momentum.
Yes.
You deposit a negative momentum.
I always thought of deposit as like putting something inside.
Yes, you put something, but that momentum has some direction.
All right.
I think we agree.
Yeah.
Okay.
It was
just the semantics,
yeah.
Right? Okay. Everybody agrees? Yes. So that deposition can be expressed with this, okay? Like, let me call this VB. The velocity of the ball, like minus gamma times the velocity of the ball. What do we call this term? Drag. Yes. Okay. It's very ugly now, so let me write down it one more time. Can I use v dot? Do you understand that it's the ball's velocity? No, I can't. Okay, minus gamma v ball. So this is the drag term. And there is one more term because of the collisions, which is basically random kicks, okay, plus some random force. This is the random force. Why? Because you have kicks in all directions and you have to account for that. So this can be called fluctuation. And this is dissipation. It turns out that the two has some relationship. So the size of this force is related to this gamma. Okay, does it make sense at all to you? So first of all, what do you think the shape of this fluctuation should be, the random force? Like the size of the force, size of the random force versus the probability. What do you expect? You always expect, in these cases, you always expect a Gaussian. Do you agree? The problem is what is the size of this Gaussian? What is sigma? Okay? So basically, we write it in the following fancy way. So first of all, the average of R is what? 0, right? The average of R is 0. What about this? So this is an assumption prime should be equal to let's call it a G times delta T minus T prime. Okay, are you familiar with Dirac delta? So this formula just tells you that if T and T prime are separate enough, then the next kick has nothing to do with the previous kick. Okay, but what G represents is the size of the kick, how big the kick is. And if you do all these calculations, like you do them properly, blah 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 blah, you arrive at this beautiful formula. You realize that G is in fact square root 2 gamma kBt. Okay? And the whole equation now is called Langevin dynamics. Okay? So, what I haven't derived, but I will show it numerically. And this is an important thing. Yes, but I also want to see this. So anyways, okay, doesn't matter. So m times v dot is actually equal to minus gamma v, okay, plus square root 2 gamma kbt times the random force. But this time, this random force is actually a Gaussian with sigma equals to 1, because we account for the size of the kicks over here. So far, did it make sense to you? It's very important because in a moment, first we want to validate that this is in fact this. Okay, then we will actually remove all the 1,000 particles that were kicking. We will just use this equation and we will see the same behavior. So it's very important that you can just integrate out all those other degrees of freedom. Okay? Do you see what's going on? Very good. So how can we validate it? So that's over here. So what I will do is, so this is the case 0, ball not moving. Okay, I will explain everything, hopefully. Case 1, ball has Vx equal to 0.1. And case 2, ball has Vx equals to 0.2. Okay, the rest is the same. And this one will record forces for case 0, etc. Record forces for case 1, case 2. So let me show you how I'm recording stuff. So in this case, I will assume that the ball is actually just bouncing the particles off without including its mass or anything. So bounce from ball while keeping temperature constant. So do you remember our previous lecture? We did some mistake, and that mistake led us to isothermal process. Like we didn't account for the velocity of the ball, for the velocity of the wall. Okay. Now we don't account for the velocity of the ball, and this term comes out, and we are doing it intentionally because we want the temperature to remain the same. And here we record the forces, the kicks that the ball would get if it was moving with 0 velocity, with 0.1 or 0.2. What we are going to do is we are going to see the size of F0, which is just the size of the random kicks. What is the sigma of it? And we also will see what is the average force on the ball when it is moving with certain velocity. Okay? I hope it makes sense. So now I did it before, by the way. Don't worry, we will not run it for 20,000 times. Each time step is 100 times, so it's like 20 million steps, I think. So by the way, we are going to average out Q steps, and each step will have 0.1 time. So 100 times 0.1 is 10 seconds in this universe. Okay. So I did it before, and this is you can see that at the end I save all the data. By the way, you can save all the data in the workspace by this line. Now I will read that data. Did you follow so far? I hope you did. Then what I do is I make the histogram of F0 divided by Q times dt. So what this is showing, momentum, average momentum divided by the time it took to get that momentum. Okay. So, and what is this? Can you just look and try to understand this?
Are you pulling the gamma term from the equation?
Yes, like gamma was the average force. Let's see where gamma appeared. So you remember we had like the case, let's say 1, which has Vx equals 0.1. So we are expecting that the average force in the x direction to be minus gamma Vx. So we can take gamma from there, okay? And then we will calculate sigma. How do we calculate sigma? We take this gamma, we put it in this formula, 2 gamma kBt, and that will give us the possible sigma of the Gaussian. So we are numerically validating what theoretically is already done. Let me run this. So you can see that the expected sigma is, for example, we did 2 cases, right? one of them yielded gamma to be 177, the other one 177. Okay, so we chose two velocities. Both of them gave the same result. Are you following? Let's see if the sigma the size of the fluctuation is also 177. So I will plot this BVX versus PVX. You are already familiar with this, right? BVX versus PVX. And I will fit it to a Gaussian. You can see that it already has the Gaussian shape. So what is a Gaussian? It's x minus mu squared, right? Divided by 2 sigma squared. So what is sigma? You see 174. Not so bad, right? I also want to point out that all these approximations that we assume, like, for example, the forces are not correlated, etc., they are not perfectly correct. So you might not get a perfect result. But maybe you didn't, maybe I went too fast, but let me summarize. So using this equation, I can get rid of all the small particles. I can just take one big particle and just give some random numbers with a proper size, proper distribution. And that will help me to analyze the motion of the big particle. So let's actually do that. Here I'm doing that. Do you see how much shorter the code is? Right? So I will use the same gamma that I got from here. What is the gamma? It's around 8. Do you see? And what is sigma? Okay, sigma can be expressed by 2 gamma temperature divided dt. What about the temperature? What is temperature? Let's see. It's constant at 193, so I took temperature 2. Are you following? And it took much longer time in the previous. Do you remember it was moving slowly? But in a blink of an eye, I will make like 100,000 steps. Just there you go. So this describes the motion of the big particle for very, very long time. And you can see that it's the typical Brownian motion. Do you see it? Everybody.
So the effect of the smaller particles are already inside the formula.
Yes. Yes. Isn't this impressive? So you don't need to always model these things putting all the particles. You can just use Langevin dynamics. To some extent, it's correct. Now, I promised one more thing, and that is connecting also diffusion to this, right? What is diffusion? So basically, when you do this Brownian motion, okay, if you do it many times, basically you can describe the probability of being at the center, or of being at any point in space. So you start always at the center, but your probability of being somewhere spreads out. In fact, it spreads out as a Gaussian. Do you understand my point? So for a singular particle, maybe some of them will go directly like this, although it's very improbable. But usually they will wander around, and if you sum all these possible wanderings, then you will get some probability distribution with respect to time. And in fact, if you calculate r squared, probability of r squared with respect to time, you will find it to go with 2 times diffusion constant times time. Okay? So the radius that the particle will probably, the distance that it will most probably travel goes with square root of time. Okay? Are you with me still? Yes. One more thing, and it is called Einstein relationship, Einstein relation, Einstein's formula. It also connects, since we already connected fluctuation with dissipation, right? Fluctuation is also connected to diffusion, because the more you fluctuate, the more you diffuse, right? So in fact, they are all connected with this formula. Actually, the diffusion constant can be calculated as kBt over gamma. Okay? So what we are going to do now is we are going to let me open the next code. You remember our Langevin dynamics, right? So this time we will repeat the Langevin dynamics starting from 0 each time. We will repeat it 10,000 times, okay? And then maybe I didn't write some comments here. I'm sorry about that, but did you get the point? So let me at least do it over here. So this one will calculate the variance of distance from the center. Okay, what do we expect it to be? Yes, we expect it to be this, right? So if I plot time versus variance, it should be like this. And the slope will give me 2D, yes, the diffusion constant, right? So let's do that. Yeah. So how many time steps I'm taking? 10 million, right? Because I will repeat it 10,000 times, and each time I will go 1,000 steps. And variance will keep adding up, and then I will take the average of the variance, and I will plot it with respect to time.
Can I ask something?
Of course.
I couldn't understand why you are differentiating the amount of steps and time, but not writing them as a whole. I mean, for example, why is there like 10,000 steps and 10,000?
Yes. Thank you.
Sections of time.
Okay.
We don't just choose our steps at amount like 10 million.
Okay, I understand you. So what I'm doing this time is, each time, do you see here, like trial? I'm doing trials, Q trials, and each time, each trial starts at the center. It's a random walk, right? So I start from the center, I do the random walk, then I put it somewhere, the data. Okay? Then I do another random walk, I put that data somewhere. Then I sum all those data up. Okay? That will give me the probability. No? Let me repeat. So let me show you this one. This is one random walk. Okay? Just keep watching. This is another one. This is another one. This is another one. So I will do these random walks. I will. Do you understand what
you are making different walks in different time
yes.
intervals and recording all of them to reach a distribution.
Yes. Yes. Okay. So I will reach to a distribution. In particular, I'm taking the recording of the variances, how far it went, the particle at each time step.
I just thought we were doing one single walk.
No. So then, if I plot time versus variance, I'm expecting it to be temperature over gamma, d to be temperature over gamma, and this is the fitting. Okay, let me just run it. 10 million steps, but it will take not too much, hopefully. Okay, you can see that there is no sign of randomness anymore once you have taken 10,000 times the same thing. Time versus variance is a perfect line, right? And the slope of this line actually will give you 2D, so you have to divide it with 2. And you can see that the diffusion constant calculated from kBt over gamma and from fitting this thing are the same. So I hope numerically we were able to tie up all these different concepts, right? Fluctuation, dissipation, and diffusion. Okay? So let's now do one more thing. Do you see that it's strangely fractalic, the random walk? Actually, the random walk has a fractal dimension of 1.5. Okay, it was shown theoretically. So let's just quickly calculate the fractal dimension with the same procedure we did before. See, nothing that I'm telling you goes to waste. We learn something, we use it immediately. So you see the same plot, like with respect to the logarithm of the measurement size. Do you remember? We had some region where it's linear, right? So I will go from 0 to 1 maybe. I will do it again, and I will do the precise calculation. And sometimes it turns out to be 1.5, around 1.5, sometimes not. But I think if you do it many times enough, at the end of the day, it's a random thing. So let's do the linear plot. Yes, 1.62. But this is random. So I have 7 more minutes, so I want to talk about friction. And friction is a very old problem. There are Da Vinci paintings. Da Vinci tried to solve friction. In particular, he wondered why, for example, if you take something like this, pull it, he would call the friction is independent of the surface area because there was no such thing as the force. Okay, he would say like friction, not friction force. Do you understand my point? So it's that old problem. So if you do it this way or this way, it's the same friction. You understand? But okay, this one was solved in I believe, 1940s, people realized that there is an apparent surface area and the contact surface area, which are different. And the contact surface area actually depends on the pressure. So that was solved. But I want to talk about the velocity dependence of the sliding friction. Okay, let's say you have something like this. And usually in real life and in many physics problems in high school and in the university, we assume that the friction coefficient is independent of velocity, right? However, if you approach it in the way we approached the microscopic friction, do you remember? It was minus gamma v. So it has to go with velocity linearly. But what is missing? So how come friction is independent of velocity? So the explanation for this came by Fractal and Tomlinson, that who devised this model. This is actually from my thesis, so you can go and read. It's very well written. So basically, the thing is that there are two main actors here. One is the corrugation potential, how corrugated is the surface, and the spring constant of the edges that are interacting with it. Okay. So if, for example, let's draw this as a potential, and this is the kx x squared over 2 of the spring. Okay. If this curvature is higher than this curvature, okay, in this case it's lower. So if you sum this kx squared with this one, you get two minimas, and as you move the spring, this object actually jumps suddenly from one place to the other. So even if you are moving really slow, there will be this it will be stuck, and then it will slip, and you will create most of the friction during the slip, and it will be velocity independent. Okay, but if this spring is strong enough, then you will always have only one minimum, and this object will follow that minimum, and the friction will be linearly dependent on velocity. So let me show you the model. This is the model, and I actually have over here the conditions and etc. Let's just watch it. Actually, this one, so you get, I have 2 minutes. Sorry, I will not tell this in full detail, but do you see it's stuck, then it actually slips. It has triple slip actually. Okay, then it is again stuck, and then it moves, etc. So let me show you the graphs. This is the graph that you have just seen. If you continue this, it looks like this. And let's see the k's. If you are above 1, if k is above 1, then the spring is stronger. So you can see that the average friction force is linearly dependent on velocity. But if you are below k equals 1, do you understand my point, everyone? Then even though you go to zero velocity, you go to finite friction, right? And these ones corresponds to triple slips and double slips. Suddenly the friction drops.